We are happy to have Alan Kiplinger from the University of Colorado. Alan got his PhD at the University of Texas, where he was studying accretion disks, and then went to NASA Goddard Space Flight Center and was doing quasars and clusters of galaxies. He says he likes things that go bang. And he came to the University of Colorado, the Astrophysical Planetary Sciences Department several decades ago, and has been here ever since. Now he's in the Center for Integrated Plasma Studies and will tell us about very high energy solar particles and the Kiplinger effect.
Well, thank you very much. And actually at Goddard I was studying the sun. I went from my postdoc work up in Pennsylvania directly to Goddard and started working for the person named Brian Dennis, who was principal investigator on an instrument called the Hard X-ray Burst Spectrometer. And it was a good instrument, and I want to talk about it a little bit. He also now is the principal investigator for RESI. And I was working with a great team of people, including Doug Biesecker. He was at ATX-RBS. And it's a scintillator, not solid state like RESI is now. It had fair spectral resolution, but nothing compared to what RESI can do with its germanium. But you see it's about a foot or two long, and it's got multipliers on the back of the scintil detector. Oh, I need the, you gave me the laser pointer, I think. Oh, looks like an ink pen. Let's see. Let's see, there we go. A little bit of light. Yeah, there's the central detector about 4 or 5 inches across, but it's surrounded, it's cesium iodide surrounded by cesium iodide. It's down deep in a well. That means this is called an anti-coincidence detector. So if you get a cosmic ray or a particle coming through the whole detector, it'll light up in the shield and it'll light up in the central detector. You throw that photon away. You only really see things coming right down the bore sight looking directly at the sun. So in terms of background, it is better than RESI because it's not shielded. And this was a great advantage. There's also the right energy range for what I was doing. And I was working with another person, an advanced programmer, Kim Talbert, who also right now is instrumental in working for, she is instrumental in working with RESI, and kind of somebody they could hardly do without. So thank you, Kim, if you're listening. We invented a routine called automatic data comparison, and it did automatic spectral fitting with this instrument. But let's talk about what the instrument has to go through anyway. This is a RESI light curve with no flares, but this is a whole 90-minute light curve, and it's interrupted often with the South Atlantic anomaly. It's in the South Atlantic, and it's very high energy particles where the part of the Earth's magnetosphere just happens to be too close to Earth. But also look at the background fluctuations. Here we're going into the SAA for a few minutes, then we shut down because it's so many particles, you don't want to damage anything. And then you can see the undulations of the orbital background. Solar maximum emissions hard X-ray spectrometer didn't have nearly as much fluctuation, so background wasn't so difficult to deal with. And what the automatic procedure did, we see a flare right here. It would select background intervals on both sides, do a linear interpolation, do deconvolution of the spectra, and I'll show you what they look like. But first let me explain what is that in focus? I guess it is. Okay, this is a big solar flare in soft X-rays as measured by GOES, right over here in Boulder. You see this is a Boulder plot with the Space Weather Prediction Center. That's where Doug works. And a big solar flare, and this is kind of like the Richter scale. It's logarithmic. So a very low level here, it has 2 channels, A level, B, C, M, and X, and then bigger than X. And I know a lot of you know this, but some of you are instrument builders and may not even know what all this means. But this is the 1 to 8 angstrom soft X-ray flux, and this is 1/2 to 4 angstroms. So this is higher energy. And to me, the mnemonic I use, and I want to know if anybody knows themselves, C, like common, M is major, and X is extreme. That's That's how I think of it. Does anybody know how they got the letters? Nope. I don't either. But at any rate, this is called an X1, 2, 3. That's about an X5 flare. The largest flare I've calibrated of all time was an X33. That's the largest flare of all time. That was October 3rd, 2003. So I wanted you to know this terminology. This is the typical 3-day plot that's produced here in Boulder every day. Are they doing that now? Are you? That's essential operations, yeah. Okay, good. And this is the corresponding proton plot. That big X5 flare, it was just right at 0 UT on the 7th, and it just preceded this slow rising proton event. And this line here, that dashed line, is the SEC, or the space weather level of being important. It's 10 protons per second per steradian at 10 MeV, and it has to be up for 15 minutes. In that case, it's interesting to NOAA. I find even little ones are interesting on a physical basis. But is Ernie Hildner here? No, that's too bad. Because the reason I'm giving this talk is largely his fault. He was the director. He was the director of Space Environment Lab and SWPC and all this. But let me show you now some hard X-ray, a couple of hard X-ray spectra and flares. This is a hard X-ray light curve after it's been fitted with the power law. I'll show you what that means in a minute. This is the beginning phase that people have generally called impulsive. And this is spectral index is the other line here. Now let me show you what the spectra look like at this particular spike. Point A at the very beginning of it, point B and C. So here are the spectra. On the beginning, there was actually, it looked like it was more intense, but in reality, the spectrum is rather soft. The slope of this fitted line is steeper. Now, this is what's called a power law. What that means is the flux equals a constant times energy to the minus gamma power. Gamma is the slope of this straight line. And that's steeper than the middle, which is a flatter line, and then the decay is even harder. This is what's called soft, hard, harder. And this spike right here is the most intense, progressively hardening spike in the whole data set of 11,000 flares. And it's the most, it is the most intense. But notice how the numbers, they go from about 4 down to 2.5 or something. The spectrum hardens across the spike. Not true for this one here. It's softest right at the very peak. And let's see. This one here is a very clear, sorry, I'm a little shaky. Soft, hard, soft. See, it's exactly different behavior. That's all I need to know to classify flares. I don't like the terms impulsive and gradual because this is a better definition for me as a working definition. And notice this little, it hardens here, and then there's some things going on. There's a little flux peak out here. But just before it happened, you see the spectrum dramatically softened. This is an injection, to me, an injection of low-energy particles. It's a softening caused by something going on. And there the spectra again. Notice the spectrum is not really fit very well by a power law. It actually fits a thermal distribution better. If you do thermal parameters, you adjust that curve a little bit. It gets a little more rounded. It fits the thermal Brewster-Long of about 400 million degrees. So to me, I've seen a lot of spectra of that hardness, and to me, I was telling people here at HAO, I said, yeah, if it gets cooler than about 400 million, I kind of lose interest. But that's the way it is. Let's see. Yeah, I have some other slides. I want to, I guess I can leave that up. I think I will. And show you. I brought some view graphs because these are professionally drawn plots. And they look a little better one I can show on that machine, I think. And also I had them. I didn't have to recreate them. So let me show you a couple more flares that are pretty remarkable. X-rays from SMM. Don't want to stand in your way. Let's see. Let me stand off to the side if I can. Over here a little bit. Oops. So the top curve there is counts per second, photons per second. And the second curve is the fitting parameter. That's the actual flux at 50 kilovolts. And let's see, here's my pointer again. There we go. And the bottom curve is spectral index. And this flare shows both characteristics, like the other one did. The beginning phase, the beginning part of this is soft, hard, soft, a little bit. There's not too good of impulsive characteristic here. But the very first, this spike here clearly hardens. This one is very clearly hardening. This is a different flare. I can't remember the date on it right now. But it was associated with those interplanetary protons, like I showed you in the plot of the orbit of Ressi. And so, of course, was that last one, the previous one I showed you on the machine, on the computer. I got two flares here to show you this way, I believe. Not this one. And I want to show you this one because it's also remarkable in some ways. It also is a proton event, a major proton event. But look at the very first main spike. I didn't get the spectrum here. There weren't enough photons for the routine to pick up a spectrum. But look at that peak there, hardening right across the very first peak. There is no, quote, impulsive phase. It's just soft, hard, harder. That's all we see. A lot of flares do this. A major proton event. And every spike of this flare has a progressive hardening, a major proton event. Turns out the largest ground level event of all time was only an M2 flare, but it's the largest neutron ground level event as an M2 flare. Every peak, I believe, was like this. And what's going on? This flare, though, is really trying to tell us things. Again, a major proton event. Backwards. And maybe a touch of this soft, hard, soft right at the very first spike or two. But these two long duration peaks are, look at the spectral index here, getting hardening on part of these, especially that decay there. But as soon as this one starts up, there's an injection, a little softening, a little injection, I believe, of lower energy particles. And then monotonic hardening until the next injection. And again, just a little touch of softening and then monotonic hardening. This thing keeps getting harder and harder and harder with time. And even on the decay, some of the flares, they may not even show a hardening peak, flux peak. They'll show just a decay like this that hardens on the decay. Had this one not happened, that would have just gotten harder and harder out here. Again, a late injection of you see this softens up just before the peak. We're injecting some low energy material, and it immediately softens, but then goes back on its old hardening path again. So this is a very energetic phenomena. We get GeV, neutrons, protons, and I was with Chertok at Sacramento Peak one afternoon, a Russian scientist, and he was bringing out plots. This is several years ago. I tried to dig it up, but I haven't found the paper again. But he showed GeV neutrons that come directly from the sun, across field lines, directly to Earth. And I worked back the time of when the particles were produced at the sun, and they occurred during one of these flux peaks. That's when the neutrons were created. Now, how do you get a GeV neutron? During this talk, I'm going to be giving you several unpublished results. One of them is I've been talking to Tom DeGrand at physics. He's a particle physicist. And I went to him and said, Tom, I'm getting GeV neutrons. How do I get them? And Brian Dennis even said, oh, you get it probably from GeV protons, because you can't accelerate neutrons too easily. I said, well, how do you do that? And he simply said, well, the best way I can think of is charge exchange. You fire a high energy GeV proton, or 100 MeV, or whatever, fire it into a helium nucleus. And it can spallate, and the proton goes through the nucleus, probably who knows what the byproducts are, and it can drop off its charge and become a neutron at the same energy. And this is a charge exchange process. It's not published. And if there are any particle physicists here, Tom suggested I ask, and if anybody has any ideas, I'd like to know more. But it's a possibility how you get GeV neutrons. Okay.
What's that energy compared with the binding energy of the nucleus?
I don't know. He didn't seem to think there's any problem with doing it. He said this is the kind of experiments people were doing in physics labs like 30 years ago. It was done in laboratories. But he thought this was a reasonable range to have it happen. So I don't know. I suspect it blows it. I suspect you get some tritium or some byproducts. Well, let's go on and see what kind of results I got. What is now, I did this work 15 years ago, or 16 years ago even. And now it has been renamed by Hugh Hudson, the Kiplinger Effect. And this association of soft, hard, harder with interplanetary protons. It's not just soft, hard, harder. It's also long delays. But what might be going on? Okay, this is one reason I like view graphs, because you can play with them. And that yellow is the sun, and the green is the Earth, and the line of sight between them, path that neutrons might take. And let me get this up higher. From the Earth, the sun has a east and west side. And the magnetic fields from the sun would go straight out if it wasn't rotating. But because it's rotating and particles are going out those field lines, it gets the Archimedes spiral type effect, and you get kind of the lawn sprinkler effect, and particles tend to follow curved field lines. And let's see. So that drawing there shows a well-connected flare. You have to be about west of the central meridian. You have to be around west 40, 50, 60, 70, 80, somewhere in that range. And the particles could potentially come right out the field lines. But in addition, I know what happens with the major proton events. They are caused by interplanetary shocks due to coronal mass ejections. They've got to be fast, maybe 1,500, 2,000, even faster. And I'm interested in what the new coronagraph is going to do here. We'll talk about that a little bit later. But these are well connected. And that dark line there is trying to show, okay, this is the flare core. And I think maybe my flares, the soft, hard, harder, are actually allowing some particles to go out open field lines. That's my theory. I'll show you later. But if the, no, this is this way. If the flare was very far east, see something like this. If the sun was very far east, these field lines that were connected, would have been connected at that other rotation, they're not connected anymore. But what you start to get is a coronal mass ejection blowing off, and coronal mass ejection shocks have no trouble crossing field lines, so that as the shock goes out, it spreads out and starts to affect and accelerate particles at the leading edge. And you can see that's what those little dots are. That whole area could be affected with interplanetary particles. That is not a well-connected event. But that is, I think both occur at the same time, or can occur. And several years ago, Gosling said, there's a new paradigm. Flares don't do it all. CMEs do essentially everything. They do all the shock acceleration. Yes, you're more than 10 protons per second per steradium. If you get 50,000, it is not directly from the flare. It's from the shock front going out at thousands of kilometers per second. That's my belief. I fully concur. It's just that occasionally I believe we are connected. But here's the result of the studies that I did. Oh, back to this. And a little bit out of balance today. I'm sorry, I'm a little bit tipsy. Just because, oh well. Let's go back and let me show you the results. I looked at all flares over 5,000 counts per second, looking for progressive hardening. Here's the central meridian distance. Here's the east, here's the west. The black dots are normal soft, hard, soft flares with no, soft, hard, soft with no interplanetary protons. And here's the GOES X-ray flux. This is the X level. This is the M level, and this is down in C level. And the dots have no geoeffective consequences. The black squares are ones with progressive hardening, either a long decay or a soft, hard, soft, and their locations. And you see the ones in the east, the ones in the east can be weaker. The ones in the west can be weaker. The only three I saw in the far east were big X-ray flares in terms of soft X-rays, but they also had progressive hardening. Let's see, the X's are misses. I would have said, okay, we see progressive hardening. There are only about 3 of these X's. It means that we didn't get any particles. The squares are where we did get particles, but I didn't see the hardening. And now, because you've seen that diagram that shows locations of where maybe particles could come at us. Yeah, I showed that. That's what I already showed. What can happen? I conducted another study because I realized that a third of the flares with high energy protons, as determined by the space weather predictions people, a third of the big ones were below my 5,000 counts per second. So I took it on down further. I went down, I found out if I go down to 800 counts per second, I will get the big ones. I'll get all of the major proton events. But then I did that with just looking at the counts per second. I didn't look at the X-rays. And then I tried to promptly forget which events they were and went back and did another study. And I did a 1 out of 3 study. There were 600 of these flares. And 600 of the flares, I did a 1 out of 3 study and projected the 2/3 that I didn't look at because I didn't have time. I didn't want to look at 600 flares additional. I looked at 200 or 158 or something like that. At any rate, this is the I'm getting ahead of myself. This is the results of that study you just saw in that previous plot. I had 130 events total. 24 showed progressive hardening. 18 actually had protons. 128 had the soft, hard, soft. And 124 of them did not show any proton event. 4 of them did show protons, even though it was only soft, hard, soft. So this table represents what is now called the Kiplinger Effect. And I published this in 95, but I probably did the work in 94. But I did do a follow-up study. What I said was correct. I'm just a little bit out of order with it. I did go below 5,000 counts per second. Yeah. Oh, I'm sorry. And here we go. Let's see if I got it. Go the right direction. And I found more events out of the 1 out of 3 study. I'll show you those results in a minute. But this is a direct plot out of AutoDCP, the program. And again, instead of 350-second long spikes, I've got 5-second long spikes. This was a small proton event. In fact, 5.3 seconds, that is the shortest duration one in the whole data set, as far as I can tell. This is marginal to say what this thing's doing. but definitely 2 5-second spikes with protons. So the time scales of soft, hard, softer goes from 5 seconds to 350 seconds. The time scales of impulsive, the soft, hard, soft, they go from 1/4 of a second to 70 seconds. They really overlap a lot. So just saying, oh, it's 10 seconds long, it's impulsive. It's more than that, more involved. This is the hard X-ray time scales. The triangles show the full width at half maximum of these first big flares that I analyzed. It shows the full width at half maximum of the longest spike. The X's show the E-folding times of the decays. And the lines connecting them, that's when you had both. Only 4 events, 4 or 5 events did that. So those are the time scales going from seconds to hundreds of seconds. And the line there is a cubic fit. It's not a fit, it's just a cubic line. A reason that if you have some acceleration site and it's expanding linearly in 3 dimensions, then you might expect something to do with time scale and the cube of the flux. See, the y-axis here is how many protons you get per square centimeter and all. They're the units. So your biggest proton events tend to be associated more with the longer duration ones. And that is a cube line that kind of makes you think the bigger, the slower. Okay, any questions? So those are the results for that. But I noticed that that last flare I just showed you with a 5-second spike, it is actually from one of my other studies. It comes in about right here at 0.1. That's as faint of protons as I could see with the IC3 satellite. A good satellite to use for this study. Okay, here's my results of the 1/3, 1 out of 3 study and the original study. And the results are, I was actually trying to predict SESC proton events. Let me go back up here and show you this. I threw in, from the first study, I threw in selection effects. I said, okay, if it's east of East 40 and bigger than X1, call for protons. If it's in the west and the half width was greater than 70 seconds, or the E-folding time was, if it was hardening at all, call for protons if it's a western event. So I set up these are the results. 95% of these predicted events, SESC predicted, I hit 22 out of 23. And out of the 700 projected, I missed 8, or 1%. And no event predicted for, there was one, let's see, no event predicted, 23, and it was an event, 23 not predicted, and then 1 actually had an event. And it had I done them all, I projected 98% correct rejection. But Ernie Hildner, I actually put Ernie Hildner is at fault here a lot, because when I first was doing this, I'd done a paper with Ed Cliver in the Air Force, and I knew about this association of soft, hard, harder, and protons. I believed it. And then he came to me, Ernie said, Alan, what can you do with hard X-ray flares to predict solar flares in general? I said, Ernie, I don't know of anything I can do with hard X-ray flares to predict flares. But if all you want to do is predict protons, and I said, yes, I think I can do it. And then he said, prove it. So I did that, and this got published. But then, no, wait on that. Then I did I went ahead and finished the 2 out of 3 study. And just to make a long story short, I did another 400 flares. But I didn't do them alone. Ernie said, it can't be just Alan, you can't be the only one that does it. So I had access to a Air Force Army captain and forecaster, Paul Garrett is his name. And he independently looked at the 400 flares with me. We got the same results. He and I got the same results. Bernie was worried about objectivity and being able to see these things. And Paul and I got the same results. My wife was mediator, and we predicted 12 new proton events. Well, it turns out it was almost a complete hit. Out of the 12 events we predicted, 5 were bona fide big proton events. 6 were smaller. They were under that level of 10, but they were proton events. So we got 11 out of 12 were proton events. We missed 1. We had 1 false alarm, and we missed no big proton events with the predictions. Yes?
So I'm struck by the sheer quality of these numbers. I mean, those are really impressive statistics.
Thank you.
And my question is, if the protons come from something in interplanetary space, as I understand it from the CMEs, wouldn't you expect that to be worse than that?
Yes. That's why, the real thing is that there's a strong association between the type of flare I'm seeing and interplanetary shocks. And the reason it works on eastern flares is because it's the CME doing all the work. I just happen to see it on the sun. So I see the solar effect, the Earth sees the geoterrestrial. And
Does this worry you?
no, not at all. Not at all. I'll show you why. Let's see, what time? How long am I doing on time? Oh, good, good. I have not timed this particularly, so I don't want to run over. Here's something. This is on Hugh Hudson's paper that first coined the term Kiplinger Effect. Maybe you can read that, but if not, soft X-ray image from Yoko, a 2000 flare. The tip of the cusp, right here, resembles a coronal helmet streamer, and such a cusp is often taken to indicate the presence of a large-scale current sheet, but may also have a geometrical origin. The scale is roughly 1 solar radii from the picture. I've got these lights. Can you turn the lights off? No, it's okay. Yes. You get an idea of scale here. Because this dark band up here, that is the north pole of the sun. And you get an idea how big the sun is here. This is a huge structure. The point is, it was the real flare that formed this thing happened 24 hours earlier. This thing's just hanging around for 24 hours. And it looks like there may be open field lines going out this way. I can't tell you whether it was progressively hardening or much about it. There are long duration events. There's another shielded detector that is associated with the Fermi satellite. It's called the Large Area Telescope. It is a shielded gamma ray detector. And I just was looking at plots a couple days ago. I don't have any with me right now that show 100 MeV events lasting 12, 14, 18 hours. You just see the rise, the peak, and the decay. 18-hour event at 100 MeV. And I can't tell you right now, this one thing I want to pursue. What do the hard X-rays do? Hard X-rays do not last 18 hours. Gamma rays do. But what's the relationship? Maybe it's one of these guys spouting off for hours and hours and hours. Huh? Is my mic on? Uh-oh. There it is. It did fall off. Sorry about that. Okay. Yeah, the microphone fell off. It's a good system. Okay. Let's see if I can read this. This is the Kiplinger Effect as published by Hugh Hudson in his 23-page review paper. I started reading the first 12 pages of this and stopped. Had I read one more page, I would have noticed this in 2011. But the extended phase of a flare is a site of one of the major mysteries in this CME SEP environment, solar energetic particles, namely that we call the Kiplinger Effect. So SEPs are associated with a particular soft, hard, harder spectral evolution in this phase. This distinguishes the hard X-ray behavior from that seen in impulsive phase, or soft-hard, soft. The implied association is mysterious because SEPs, according to current consensus, originate mainly in diffusive shock acceleration at the CME-driven Val shock. There should be no direct connection between the process and corona where gradual hard X-ray sources appear. Specifically, no magnetic connection should exist within the standard model. Well, I don't necessarily believe in the standard model. But the RESI observations have, these are RESI flares, and you can see the numbers up there. For instance, on no soft harder, 0 predicted, and 19 were not observed. The RESI observations have now convincingly confirmed this association by Grayson, Bob Lynn, and I'm trying to remember the third author, as shown in Table 2. That was the first naming of it. Ed Cliver, in this 2012, republished this same table, but he messed around with a couple flares and recategorized them, but he got the same effect. He labeled it the same effect name. So I didn't do this. They did. After 16 years for Hudson and 17 years for Kaler, and now apparently it's accepted. And it's a good feeling. I don't have to prove it anymore so much. It's a very good feeling. But what's going on? This is my cartoon for it. And I thought of this before I saw Hugh Hudson's beautiful photograph he brought in. I figure we do have a very high structure with a cusp at the top where there's energy acceleration. Down below, right under it, may be the impulsive loops, the ones that are directly connected. The particles get accelerated along the field lines. They go down. They produce gamma rays, hard X-rays, and they're smaller. These may only go up 15,000 kilometers. These may be up Yoko data, or mainly Hinatori. That was the first time I saw it in 2001 with these hard X-ray flares. Show a very high cusp up here at 50,000 kilometers, maybe 60,000 kilometers, and RESI has done more of this. I've not done much RESI imaging yet, but I'm getting much more interested as time goes along. But my picture is a current sheet going up with open field lines connected to Earth. And Joan, you can tell me, aren't CMEs typically associated with the sides of to the side of an active region and not directly symmetrically over it?
The study by Harrison is the one.
Speak up a little. Yeah.
And what he found was they tended to be on the side, but that's not, that was the selection we had in that sheet. They're not always on the side.
But just, I know a lot of them are.
So I think there's a solar cycle for that. For instance, in the rising part of the cycle, you're going to tend to get the active regions on the forward side of those helmet streamers.
Mm-hmm.
That's where they rise at higher latitudes. So there's partly a solar cycle.
Okay. All right. So at any rate, I picture a CME off to the side, perhaps, and directly it's expanding upward, outward against the current sheet, and maybe if there's any particle people here, I need help. And but is there any, I did talk to some people with my Center for Integrated Plasma Studies, ask them physically, can we push material into a current sheet that then gets driven? You see, if the electric potential keeps building up over time, and you throw in some material, it has a hard X-ray spike that's progressively hardening, and then you lose all your particles. Okay, you do it again. That's why I get two big humps, maybe, that are following the same acceleration curve, the same hardening. I'm actually, this may be completely wrong. I don't know. It's just my thought that maybe the CME is driving the flare itself, or some of the acceleration. And then the ones that are well connected, we can sometimes get direct particles from them. Oh, I didn't tell you that the real long one, that one I showed you with the two 5-minute humps, the 350 humps, 350-second long humps, the very first one had high energy protons. Oh, they both did, but I guess. I went to Ron Zwickel at Space Environment, and I challenged him. I said, I know when the hard X-rays were produced and when I think acceleration's occurring. And we had a very fast rise of protons. He went back and determined the path link and gave me the exact time of when the protons were produced at the sun. They occurred in that 5-minute spike, dead centered on it, plus or minus 3 minutes. That's when the protons received at Earth first began appearing at Earth. They were produced during that hard X-ray hardening spike. And that's partially what makes me think there might be something like this going on. SMM, I'm not going to RESI right now. I'm going back to some of the first. I want to talk about gamma ray lines. What are they? Well, there's a lot of lines. This is energy in MeV. Hard X-ray burst spectrometer typically operated between about 30 and 500 keV. Occasionally we took it up to an MeV, but we never got into this range. And there are various lines that show up. This is the first big spectrum. This is 30 minutes of integration or so. And you see carbon 12, oxygen 16, and there's a recombination. There's an annihilation line at, I thought, at 4.4. I don't do gamma ray lines as much as I should probably, but there's several lines here now. Now RESI is really resolving this with its germanium. So if I showed a RESI spectrum, it'd have nice little sharp spikes, and some of them sharp, some of them though are very energetic, and they are naturally broadened. But those are gamma ray lines, and how are they associated with the soft hard harder business? Here are the results. Again, this is unpublished, but I just want to share it. If I get run over by a bus, at least I can say, well, at least I told people. Comparisons of spectral hardening with the tables from the solar maximum mission of Vestran, published in '99, 10 years after the mission. I haven't done all the proton work on all of these, but I did look at all of the gamma ray line events. We had 19 flares. We saw gamma ray lines, but no evidence for hardening. And I looked at a lot of these, and no evidence for protons. To me, these are the soft, hard, soft, closed loop gamma ray lines being formed in the chromosphere by the high energy particles going down. 9 events, gamma ray lines and spectral hardening seen, but not at the same time, at any time during the flare. 9 events like that. We get gamma ray, and that could be my picture with the impulsive loop down below and the cusp up above. Okay, 11 events. Gamma ray lines and hardening seen are simultaneous, normally in the later part of a flare. What's going on? I don't know. I'm just throwing these numbers out because no one's ever seen them before, except in a couple of proposals through the Air Force and things I did. That's why I had the results. And here, progressive hardening occurred and protons seen at Earth, but there's no evidence for gamma ray lines at all. So it can happen without gamma ray lines. They're not essential. All associated proton events were at the SESC level or higher unless otherwise noted. So we get all types of animals here. And the other one, you saw how orbits can be chopped up into day-night, SAA, and all that. I threw out events from the beginning if they had really chopped up orbits. I didn't even look at them. And 25 events fall into that. They had gamma ray lines, but you only get 20 minutes out of a flare, and it wasn't worth me trying to say anything about progressive hardening. So I eliminated them. Well, back, I guess, closer to the end now. The reason I'm giving this talk is because I was fortunate enough to be invited to a party about a month ago or 6 weeks, and at HAO, at NCAR. Was that right where the party was? And you were boxing this up. This is the new K coronagraph that is just being installed now at Mauna Loa. And to me, this may be one of the best things since sliced bread. I'm really excited about it. It was being boxed up. It has a 7-inch lens. It's uncoated. And I asked Joan, why is it uncoated? And she said, oh, scattered light will kill you. They are trying to see, not down all the way, almost all the way to the sun at 0.05 radii, 40,000, maybe 45,000 kilometers. She's just in the range where they'll get coronagraph through the atmosphere, our Earth's atmosphere, at Mauna Loa. As I say, it's a 7-inch refractor. Down at the bottom here, they've got an occulting disc to keep the sun from hitting the whole CCD. And it's not a disc. It's a little diagonal mirror that throws the heat out of the beam. And they got one for summer when the sun is big, and one for the one for summer when the sun is small, and then spring and fall is a second one, and wintertime when we're close to the sun, they've got a bigger one. And they have to switch this out 4 times a year. But it's got a big CCD, operates at 150 frames a second. But they're not going to collect all that data. They're just going to average them there and not ship. I think you're typically going to be sending 15-second time resolution. That is good enough for most of my events. It's not good enough for that 5-second guy. But hopefully, if I can give you a heads up, and we've got it on the limb, I can say, hey, we got a region here that's been putting out these flares. Can you get me some high time resolution stuff? And she said yes. So I'm really looking forward to seeing what this K coronagraph can do. And K coronagraph, it's a German term. It means continuum. There's also the E corona, which is the emission line, and the F corona, Fraunhofer line. So there's 3 different coronas. The Fraunhofer is just dust, like you see in the zodiacal light. But this is the K coronagraph, and it's a continuum. There's no absorption lines because this is sampling the 1 million degree plasma of the corona. It Doppler shifts, it Doppler broadens everything. You do not see the absorption lines. And this is the band passes they're using. They're in the red because it's the sky is darker, but also from about 730 to 750 nanometers, they're avoiding emission lines and they're avoiding these huge water vapor absorptions. So they're in that little continuum there of 30, 40 angstroms, and that's where they'll be observing. And they'll be measuring intensity, light intensity. But from that, with modeling and all, you can actually get to electron density. And I don't know if these things are heated high in the corona, if my hardening flares are heated very high. I don't know if it's going to be a rarefaction or a condensation. But we're also going to have RESI looking at the same time on some of these events. All we need is a few good flares. And I think we can start to understand. But I'm really glad you built that coronagraph. And she sent me one of the events I showed you on the black view graph was taken by, it was an Eastern event, and there's a coronagraph from the solar maximum mission, taken around 1981, and you see this nice expanding shock front coming out in the east. Apparently, this thing came over and got us eventually. John, what is that triangle? Which way is Earth here?
The solar north is the triangle's pointing to solar north. The dotted line is the photosphere, and of course that's coming off the east limb. So, the sun-Earth line we're looking for it.
Yeah, the sun-Earth line's this way. So this
Very fast CMA is about
1,500 kilometers per second. But somehow that thing got over and got us on our field lines.
very wide. So
Huh?
it's a very wide CMA. It's about 170 degrees wide.
Yeah.
Like you say, produced a
And
shock of a very low
Kaler's paper that I put in the abstract, it measured widths of CMEs, and it found a very strong correlation between the width of a CME and progressive hardening and protons. Very strong association. And if they're too small and too narrow, then you don't get the association so well at all. So, at any rate, things are going to be even a lot better when your new one gets going. So, that's all from me. Thank you.
Questions?
I explained too much. No, I'm interested to see what the future is going to bring with combining a lot of these data sets and stereo, and there's just so many instruments now that can help, and yours is one. But I don't know the answers. Yeah?
So you said that the spectrum fit a thermal emission rather than a power law a little bit better. If you had to, and you said the spectrum
we see it flattened out on the decay, the C portion of this, it flattened out. That first peak, I said I fit it with a thermal, not because it was the best. Actually, what fits it better is a double power law. And this is, I didn't bring this up, but right here, you see it's kind of one slope to about 250 kilovolts, and then it slopes steeper. And George Dalk and Robert Wingley and I wrote a paper on this break effect. The soft, hard, harder ones break around 250. The soft, hard, soft break around 125. So almost a double, twice the power. I think this is an indication of the high energy effects going on here. So double power law works better. And some of them even do this. This is pretty rare that the break is upwards. The bottom gets fit steeper than this. And the single power law, it's kind of a compromise. They're both not great fits. The thing is, RESI answers these questions beautifully with its resolution. This is kind of a low resolution instrument. The only thing I liked about it so much was that it was available to me and had very good background characteristics. And,
So how high does RESI get up?
Other way. You look at the orbital plot here. You can see energies on the right-hand side. I'm going to get back to it. 20 MeV, according to that. But it easily can see lines in the up to 10 MeV is no problem for RESI. And it's a bigger telescope. It has wonderful spectral resolution. It doesn't have pulse pileup. Formidable energies with extremely high energy resolution. But it's an imager. It has rotating grids of tungsten. Every 9 seconds, it can take a picture. So as an instrument, and I was helping to review it at one point, as a spectrometer alone, it's a spectacular instrument, just as a spectrometer. As an imager, it's a spectacular instrument. Combine them both, that's why it's still in business after 10 years. And I hope it keeps going. You know anything about it, Doug? The lifetime of RESI?
I think they can go as long as they keep getting funded.
Pray for funding. We can't replace it. It's an Explorer program type satellite, but working very well. Has cooled germanium. I guess at some point they'll run out of coolant, but
They've done very well at the reviews.
Okay, very good. A great instrument. Yes, Paul.
This is a question out of sort of complete ignorance of solar physics and astronomy.
He and I went to Texas together.
It's sort of two questions. So let me ask both before you answer one of them. One is, what's causing the X-rays? Where are the X-rays coming from? And the second question is, what's producing the time variability in both these kinds of events? In other words, what's going on that causes SHH and SHS?
I'll tell you what I think. It's on the other view graph. The first part of this flare is SHS. And I think what we have here, we have strong magnetic fields in closed loops. The electrons are being accelerated to hundreds of kilovolts easily, and they hit the chromosphere, and it gives off electron, proton, brimstone. It's the electrons coming near a proton. It's ionized, and so they get brimstone bending around. And we are not particle limited, we're field limited. So the electric field, I believe, is cranking up to the peak, and then it relaxes as you're field limited, not particle limited. In this guy, we're particle limited. That's why I had the double peak, and it keeps hardening. We've got the electric fields. We're not field limited, we're particle limited. And it's up high altitude, low densities, maybe 10 to the 8th, 10 to the 9th electrons per cubic centimeter. So it's the soft, hard, softer, I would say it's called thick target emission. It's hitting the thick, dense target. The upper emission, I believe, is thin target. You're getting electron Bremsstrahlung, you've got electron traps. And that's a point, too, that you could just put a whole bunch of electrons in an electron magnetic bottle, and the high energy ones will stay around longer because their collisional cross-section is lower. So the trap naturally hardens, even in thin target. But there's a couple of these flares, and I tried to dig it up. In fact, I thought it was this one, but this is, and that's why I was asking Joan for some help on this. I thought that this one, there's one flare I've got. Ooh, I lost it. Oh, well. There's one flare I have. If you imagine, let's see which way. This is the spectrum. And you go soft, hard, harder. There's one flare I have that it actually, the low energies are getting lower in flux, while the high energies are rising. It's a true acceleration process. It's not just a trap. And I found that in at least a couple of flares. They don't all show it. This one in particular, you could almost say there's trapping. Well, there is trapping going on, but I think it's a true acceleration process. It's very high energy, and I think we got a lot to learn. Good question.
We should close with that.
Okay.
Thank Alan again.
A lot of fun for me.